Information on screen there. Feel free, whether it's this session or any other session that I'm presenting on, or any time in the future, to send questions, comments, concerns, whatever, to the address you see there. You can also contact me via my blog, which is also listed there, and a site that I post tips, webcasts, and blogs and whatnot on. So if you forget the email address, you can always get me there. So what we're going to talk about today is partitioning of data within SQL Server, particularly. Once I can get my... There's also many different types of partitioning for data. Many that have been used prior to SQL 2005, at least when you're working with SQL Server, are application-managed partitioning, where your data is stored across different servers to give you a scale-out type capacity, as opposed to a single all-in-one instance with the scale-up type capacity. The partitioning here is decided and routed based on application-specific logic to route data writes and reads to and from the appropriate system. There's also the concept of distributed partition views, or just partition views, in SQL Server 2000 and earlier. It's still included in 2005 and will be in 2008 as well, whereby you basically create multiple physical tables that match each other structurally to some degree, and then you union those tables together through a view. And the SQL Server takes care of routing and reading and optimizing to and from the appropriate physical table. We'll talk about some of the advantages and disadvantages to that approach, as opposed to the new approach, which is partition tables and indexes, which was introduced in SQL 2005 and will be improved upon in SQL 2008. And we'll talk a little bit about that throughout the hour we have here. The biggest difference between partition tables and indexes and distributed partition views, or just partition views, is that partition tables and indexes are a single object as far as any coding or data retrieval or data updating is concerned. You work with a single object at the relational level, and the storage engine takes care of determining, based on what an administrator or architect has defined, where that data should be routed and stored and accessed on disk, or what have you. This is what we're going to focus on pretty much throughout this talk. We are going to talk a bit about partition views and how to compare and contrast the different technologies, because there actually still is a usage niche in SQL 2005 and beyond for distributed partition views that partition tables and indexes just won't touch. So let's hit on a couple of the motivating scenarios for partitioning your data. I usually get questions in terms, from customers and clients, and why would I want to partition my data? Well, if you have 3.5 petabytes of data to manage and distribute, you're probably going to need to partition your data. 3.5 petabytes is 3,500 terabytes of information. A very large amount of data, and it's not getting to be extreme today to see customers that have manage their data in terms of petabytes as opposed to terabytes. It used to be that a 10 to 15 terabyte data store was extremely large. 10 to 15 terabytes is starting to push the envelope of medium-sized database systems in today's world. So the data growth and explosion has obviously played a part in that. A terabyte of new information or new data daily that you need to load or manage or retrieve or unload can be an extremely difficult process, and one that takes some thought and whatnot. Multiple data loading scenarios. So you have the scenario where you need to load data into an existing table with existing data. You also have the scenario where you need to load data into an empty table or a new table where there is no data existing. Similarly, you have multiple data unloading scenarios where you need to roll data out either for an entire table or only portions of the table. For example, a day's worth of data, a week's worth of data, a month's worth of data, etc. Typically, these two loading and unloading scenarios are conjoined with each other, or one occurs and then the other. Think of a rolling window scenario where you want to keep the last 90 days of information available to a particular application, for example, which we'll talk about here in a bit. So what are some of the typical performance impact or performance benchmarks for these types of scenarios? Well, in the data loading scenarios, into an existing table with existing data, if you're talking a terabyte of information, you're talking at least 10 or more hours, depending on your system. The 10-hour mark at the low is based off a benchmark on a HP Superdome system connected to a very high-end SAN. So 10 plus hours at a minimum. Of course, into an empty table with no data, you can push down into 1 hour. It's actually, there's hardware and systems available today where you can load a terabyte of information in 1 hour into a SQL Server system. But there's still a drastic difference there, 1 hour versus 10 hours. Obviously 10 times into an existing table with existing data, which is typically the scenario you're looking at with an existing application. Even if you're going to load into an empty table, most likely you're going to merge that into some existing data structure of some form. Similarly, you have the multiple data unloading scenarios. When you remove an entire table, you can do that in less than a second. You can drop the table, you can truncate the table, and it's done almost instantly. However, if you need to remove only a portion of that data, for example, 1 terabyte of a petabyte-sized data, you're talking 3+ hours minimum, likely double, triple that. So very large differences there. So these are some of the motivating factors for partitioning your data along those types of boundaries to be able to push past those 5, 10-hour operations to try to turn those loading and unloading of a portion of your data from more closer to the 1 to 5 second operation time frame. We've got some demos at the end of the presentation here that we'll discuss that. Oops, I don't know what's going on there. So the whole concept behind partition tables and indexes is basically to split the data or index structures into multiple storage objects. Keep a single logical structure with multiple storage objects, which could be spread across a single file group with multiple files that reside on multiple LUNs and hundreds of spindles, or tens of file groups that reside, again, on possibly multiple LUNs and multiple spindles. You typically partition, in SQL Server 2005 and 2008, you're only able to partition data in one method, and that's to specify a range. So, for example, you can specify date-time boundaries or boundaries for integer-based values. Date-time is obviously one of the most popular. Integer-based values or matching a particular category. For example, geography-based partitioning is fairly common as well. For example, in the United States, we might partition our data by state. So you might have for the state of Maine, for the state of New York, for the state of New Hampshire, and partition your data that way into 50 or 52 different storage structures. Again, handled as a single object as far as the relational engine is concerned, which is where you do all your querying of data. As far as the storage engine is concerned, in terms of storing that data and making it available to the relational engine for querying, it handles allocating that information across different storage structures that an administrator has defined. Okay, and we'll talk a little bit about that. So to give you a bit of a graphical view into what this might look like, here's a standard non-partitioned storage structure. You might have your order history table, a single non-clustered index, where all your tables data or your heap resides on this single file group on this single LUN, and your index resides, again, on possibly the same or a different file group on a single LUN. Very simple storage structure. Contrast that with a partition structure where you might take your heap or your cluster data and spread that across 3 separate file groups and 3 physically separate LUNs based on, for example, in this case, looks like the year 2002 the year of the order, 2002, 2003, and 2004. And then your non-clustered index similarly spread across in 3 partitions across 3 separate spindles. However, notice that this index, for example, this non-clustered index is actually on your customer ID, even though your partitioning is still on your order date, or the year of the order, for example. Building your indexes, and your indexes correlated with your tables and your table data in this manner is what's referred to as an aligned partitioning structure. And it's something that's considered a best practice and you're going to want to do to perceive some of the benefits that we're going to show here in a bit in terms of loading and unloading data. So we've already touched on some of these, but the benefits of partition tables, obviously you can handle fast deletion, so unloading of data, and fast loading of data. So again, we're trying to get to the scenarios where you're loading and unloading of existing data or into an existing table to get closer to the times for loading and unloading into an empty table, okay, or unloading an entire table. Backup and restore becomes simpler because, for example, any historical data that has not changed, that's partitioned older, doesn't have to be backed up multiple times. So instead of taking a full backup every day or every week, you can take a partial backup of only the data that's new or the data that's changed, as behind the scenes you're shifting partitions around so that the data that hasn't changed is on your older spindles. Index management and fragmentation becomes much easier to manage. Not only does the historical data that hasn't changed, it's likely also not become fragmented. So there's no reason to maintain that data, no reason to rebuild indexes across 95% of your data when only 5% of the data has changed. And of course, support for alternative storage and historical data. So similar to how you wouldn't have to back up data that hasn't changed, you could also take an approach of storing that historical data that most likely doesn't get queried as frequently as the new data. Take, for example, the last 90 days. Everything prior to the last 90 days could be on a separate partition that's stored on a separate physical LUN that is an NTFS compressed volume, which is fully supported in SQL 2005 and beyond. So then your storage becomes compressed. Those might be cheaper SATA LUNs as opposed. And then some huge benefits in terms of querying against large tables, particularly in the data warehouse space where you're querying across multiple large fact tables that are correlated together by a date range or an ID of some kind. Obviously, you have a smaller index tree. Each partition would contain its own index tree. So instead of having one large B tree, you might have 15 smaller B trees. And if you query into a single partition, you don't have to traverse this one large storage structure. You simply have to traverse and work within that one slice of the pie, so to speak, that you're concerned with. So some of the improvements with this over partition views. So we've already talked a bit about how it's a single object. Underneath the covers, it's also a single object to SQL Server. Single set of statistics across the single table. And when it comes time to compile and generate query plans, it's much easier for the optimizer to build against a single logical structure as opposed to 10 or 20 or 100 separate physical tables that each have their own statistics, their own indexes perhaps, in a separate subtree, and your compilation has to be built for each one of those. So it becomes very complex very quickly as the number of tables grows in your partition view strategy. The complexity and the amount of time it takes for the optimizer to compile a plan to actually generate a result becomes more and more difficult and more time consuming. Auto-parameterization support. Partition views do not support auto-parameterization. What auto-parameterization is, if you're not familiar, is if you write ad hoc statements from your application as opposed to executing stored procedures, and you don't take a lot of care in parameterizing those statements into parameters with values, and just submit ad hoc statements like select star from table A where column equals 2. And then the next time the same thing, only instead of column equals 2, column equals 4. So you're basically submitting the same exact statement with different parameters each time. Well, the database engine has an optimization built in where for certain types of queries, it can auto-parameterize that and cache a plan a single time instead of having to generate a plan every time that ad hoc statement is executed against the server. Partition views support auto-parameterization. So again, you have a smaller plan cache, less memory bloating on your server, less compilation time for the queries that are coming against your server, as opposed to the partition view strategy where that's not possible. Bulk loading of data. If you perform a BCP or a bulk insert against a partition view structure, you actually have to load data to the physical table that's appropriate for the data you're loading. You can't bulk load against the single view that unions all the data together. You can, but you won't get a bulk load. You'll get a standard fully logged load. Contrast that with a partitioned table, and it's possible. BCP will bulk load into an empty partition, for example, or something of that nature. Numerous fine-grained partitions work well. So like I mentioned with partition views, as the number of tables grow, things become more and more complex and slower on the server. So if you want to have very fine-grained partitions, that means a larger number of tables that have to make up your partition view. Much more complex, much harder for the engine to optimize. Contrast that again with partition table. You can have up to 1,000 partitions in a single table, and it works seamlessly. Okay? The one downside, and this is that niche that I was talking about earlier, the one downside of partition tables contrasted with your partition view strategy is that a partition table cannot span multiple databases or instances. So if you want to have tables, a structure that resides partly in database A and partly in database B and partly in database C, or take that to the next step, which is the more logical choice, part of it to reside on instance A, part of it to reside on instance B on separate physical servers, part of it to reside on instance C, which is even on another physical server. That's not possible with partition tables and indexes. It is possible with distributed partition views. So that's still that little niche where partition views today actually make sense if you're in that type of scenario. I'm going to cruise through these because we're going to talk about them a bit in the demos. But some of the basic objects that you will work with when using partition tables and indexes in SQL Server are what are referred to as partition functions, which basically define the boundary points, or where you want partitions to start and or end. And the way that would work, for example, in a date time, if you were using a date time to partition your objects on, you specify, for example, you can see here 2002, January 1st, 2002, January 1st, 2003, January 1st, 2004. And depending on whether you specify a right or left partition function, typically you probably assume that you use right. Then what this means is that everything from January 1st, 2002 and onward, inclusive here, will be in this partition. Everything January 1st, 2003 and onward, inclusive, will be in this partition here. If it was a left partition function, it would be just the opposite, which is everything from January 1st, 2002 and before would be in this partition. Everything from January 1st, 2003 and before would be in this partition. So it's just semantics on what value is actually included in the actual boundary. Well, there you go. There's not a lot of... just understand the difference between left and right. It's not overly complex. You can even pick one and use it all the time. I would recommend right best practice, particularly for continuous data. The reason for that is the boundary defines actually where the data starts. So take the prior example, January 1st, 2003. Typically what you want is all of 2003's data in a partition. To make that easiest, if you use a right range, that just means that January 1st, 2003 will be included in the next partition, as opposed to a left range, which is January 1st, 2003 will be included in the prior partition, and everything greater than January 1st, 2003 will be in the next partition. The next logical structure that you'd work with is what's referred to as a partition scheme. And what a partition scheme does is basically maps a partition function to physical storage. So for example, a partition function to a file group. Okay? There's no requirement to use different file groups for different partitions. It's fully supported. You can use separate file groups for different partitions. You can also use a single file group for all partitions. Okay, that's the way we'll do things in our demo here. The reason that it's available in the cases where you would want to use separate file groups for separate partitions, for some of the manageability things I was talking about earlier, backup, restore, being able to store your historical data on less expensive compressed volumes or things of that nature. As a best practice, and this is kind of in SQL Server in general, spread all your file groups in a partition scheme, whether it's one file group or 100 file groups. Spread them across as many spindles as possible. So for example, if you have 100 physical spindles to choose from, don't try and get fancy and overthink your storage where you take 5 file groups and dedicate 20 spindles to each file group and then try and get smart about where you're putting your data and who's going to query it. The database engine and storage platforms today, SANs particularly, are extremely smart about how to pull data and where to pull data from. If you were to ask me today for 99.9% of the scenarios how I would configure storage for SQL Server, I would say create yourself a single file group with one or many files using every spindle that you have for every file and let the database engine and the SAN or the storage hardware do the work for you. That's going to work best in most cases because otherwise you're always going to invariably end up in a situation where you're underutilizing a single file group or two, which is 20 or 40 or how many ever spindles. That could be doing work for you 99 to whatever % of the time. Did I go the other way? A partition scheme, to bring a partition scheme and the actual physical storage into the partition example that I was showing you earlier, these are all separate physical file groups. You can see they could all just as easily be a single file group. This also seems to imply that they're all stored on separate physical spindles. That isn't necessarily the case either. Like I mentioned before, as a best practice, you would want to use all possible spindles for each file group, whether it's one or many. But basically, what a partition scheme does is map each of these partitions to some physical storage, whether it's to a single file group or multiple file groups. Okay, so that's the job of the partition scheme. So when it comes to querying data, and we're going to go through a sample of some of the differences in querying, but best practices are to restrict, always try and include a filter that's a filter on what you're partitioning on. So if you're partitioning on a date time of some kind, so you're partitioning on each year's worth of data, and your queries are going to perform and scale more efficiently if the majority of the queries you write and run also include a filter on a date time. Even if it's as simple as, I know it's in the last year or the last 2 years. Okay? And I'll show you some differences between that. There are some gotchas with joining of data across partitions. If you, for example, do something like this, where your join condition is based on region ID, and then you specify the name or a particular sales region of Asia, that will not eliminate partitions that are not Asia, for example. Okay? A better way to do it would be to do something like this, where you use, for example, the region ID in your filter. So even though you know that logically in your database, region ID and region name are correlated and distinct. Region name of Asia always correlates to ID 7, or region USA always correlates to ID 5. The optimizer will not figure that out for you. So instead of using where name equals Asia, it would be better to figure that out on your own and then use the ID in your query. Okay? There's lots of other enhancements in terms of grouping and filtering, particularly, like I mentioned earlier, in large data warehouses. And then finally, before we get onto the demos, I'm going to walk quickly through some of the data loading and unloading operations in the functions that you would use there. So like we talked about earlier, loading and unloading data. Typically, the way you're going to do this if you're partitioning your data is to load data into an empty file, an empty partition and unload the earliest partition. You always want to try to load your data and unload your data on partition boundaries. Why? Because it's extremely fast. It's a metadata change only. And we'll show you that here in a bit. And you'll use these three methodologies for making sure that that is something that you can do. You can split partitions into two partitions. You can merge two partitions into one partition. And you can switch partitions. So if you have multiple tables that are partitioned, and you want to take data from this table and put it into a partition in this table, and they're aligned partitions, you can switch data from this table into this table, metadata change, and it's instantaneous. You can also do the same thing from a table that's unpartitioned into an empty partition in a partition table. I'm going to walk you through that in an example if it doesn't make sense. Shows you some of the DML that you'll use for a split. You basically alter the partition function and split whatever range it is you want to take from 1 into 2. And it basically will add an additional boundary point. So we talked earlier about how if you had date-time boundary points, and I think in the demo it had 5 partitions listed there. If you were to split one of them into 2, you would basically end up with 6. And if you split again, you would end up with 7, and then 8. Okay? To show an example of that, again here with the same example as prior, let's say we want to split the 2006, it looks like, or split off a new partition here on the end. We'd basically run this, we'd run this statement. A new partition would be built here. This is split from what was prior, the last partition. Now we've got a new empty partition on the end here, which would contain, ideally, obviously, 2006 data. Okay. Some considerations. That top one you're going to see as a common theme through all of these. You always want to be splitting, merging, or loading into an empty partition. Okay. If there's data in the partition, SQL Server won't be able to make it a metadata change only. And I'll show you an example of that. It'll basically result in the same way you would have done it before, an insert or an update. Okay. It's extremely I/O intensive if the partition has data in it, because it would be the same as, like I said earlier, you doing just an insert. Merge is just the opposite of split. So I'm not going to spend a lot of time walking through this, but it basically takes 2 partitions, merges them into 1. The place that you would use this is just the opposite of split. Typically, if you picture this as a rolling range scenario where I want to keep 90 days of data, obviously as it becomes tomorrow, what am I going to have to do? I'm going to have to split off a boundary like I did earlier to store tomorrow's data. And I probably want to drop off the 91st day ago data. Okay? So I showed split already, which added a new partition on the end. This time, let's say I want to drop off the earliest data, which is over here. I do a merge of the first range. 2002 data gets moved out, and now you end up with basically your first partition being 2002 instead of 2001. Okay, so you take the split scenario from the beginning, and that adds one on the end. The merge scenario now takes the data from the earliest partition and basically merges them into a single partition. Again, instantaneous if it's empty, I/O intensive if it's got data in it. I'll show you this. And then finally, the switch. So this is also a very powerful and is going to be used for data loading and unloading. And it basically instantaneously swaps the data from either one partition in one table to an empty partition in another table, or from a non-partition table into a partition table, into a single partition in a partition table. Okay? So take your loading scenarios. What you probably do today is you have a lot of data files that you bulk load into an empty table in SQL Server, and then you do an insert update into an existing table somewhere based on the data that's now in that temporary loading space or that loading table. Contrast that with what you would do if you were partitioning, is you would still load all that data into an empty table. So you get the performance benefit of loading into an empty table as opposed to a table that has data in it. And then you would take that single table that has all this data and you would switch it into your partition table. It becomes instantaneous, okay? As long as your partitions are aligned and whatnot, and we'll go over that. So to give you an example, let's say here we want to switch a table into a partition. So I've got this empty partition here. I've got table B. This is the partition in my table that is partitioned. This is my data in my table that's not partitioned. I define a check constraint on it, which I'll talk about in a bit. I basically run a statement to switch the contents of this table into this empty partition. It's done instantaneously. A metadata change occurs. SQL Server now points this partition to the data that was loaded in that other table. And now that data resides in that table just like it was always there, or just like you had done an insert, update, delete. The same thing, let's say you want to switch data out. So you want to take the contents of this partition and delete it from this table. You do the same thing in reverse. Instead of switching data in, you're going to switch data out. So I'm going to take the contents of this partition and switch it out to an empty table. Again, I run a switch statement. It's just opposite this time. I'm going to switch the partition 2 into table B. Again, SQL Server is going to make a metadata change. That table will now have this table down here will now have the contents of what used to be in this partition, and this partition will once again be empty. Okay? And then similarly, you can also, like I mentioned, switch data from a partition table to another partition table. So if I have two partition tables here, I've got table A and table B, they're both partitioned. I've got a partition of 2002 here, a partition of 2002 here. I want to take the data from this partition in this table and switch it into the empty 2002 partition in table B. Again, run a single switch statement. That metadata change occurs, and that data is now in table B as opposed to table A. Okay? Again, we're going to talk about why you want to have your indexes aligned and have your indexes match when we go through our demos here. So some scenarios where you're going to use this, we've talked a bit about sliding window and efficient backups. Index maintenance we've talked about, and also snapshotting of your data for availability. I talked about that a bit in 2008. I'll also talk about that tomorrow in my service-oriented architecture talk. So briefly, we've touched on this, but index maintenance, some of the new enhancements with index maintenance when you're working on a partition table is you can now reorganize and rebuild a single partition of a table as opposed to having to reorganize or rebuild the entire table. So again, take those scenarios where 95% of your data hasn't changed. Why should you rebuild it? It hasn't changed. It's not fragmented. There's no reason to maintain that index, that portion of the index. So this gives you the ability to do that. And we're going to walk through some of the speed differences here once we get into our demos, which we're going to jump into now. So I'm going to switch over to Management Studio. And first I'm going to walk you through some operations with switching, splitting, and merging. So what I've done here is created a database. I have a table in it that's partitioned. I also have a table that's not partitioned. I've defined a partition function. You can see here it's basically yearly data. So my first partition has all of 2004, second has 2005, 2006, and so on. You can see here I created a partition scheme, and I specified that all these partitions are going to go to the same file group. Okay, obviously on my laptop, what you can see below there commented out, I could have specified, for example, to use all these different file groups. I haven't set it up that way on my laptop. In a server scenario, you might have that. But here I'm just saying all of these partitions should go to the same file group, which is my default file group. Here you can see I'm creating my table that is going to become partitioned. It basically has a simple integer, a character column, and a date time. Okay, and you can see this new clause right here, which might look funny if you haven't worked with it before. But basically, instead of specifying a file group that I want that table created on, I'm specifying a partition scheme that I want that table created on. So that partition scheme I created earlier is now what this table is going to be created on. And it's going to use my date time column as the partitioning function. Okay, so we're going to partition on this DT column in my table. Then what I did is just filled up that table with some random data using a simple loop here and some queries to put in data for each of the 4 or 5 years that I had, and I created some indexes. So if we take a look, I should have about 5.5 million records, which I do. Can everybody see that okay? Okay. So I got about 5.5 million records in my partition table here. This is a new function in 2005 that's built for working with partitioned objects. And what it allows you to do, it's $partition. And what it allows you to do is specify which partition function you want and a date, in this case, a date, because that's what I'm using to partition that function on. And it will tell you what partition within that object that a record with that particular date time would go to. So if I query this, you can see that what I've said is 2001, that would end up in the first partition. 2002, that would end up in the first partition. 2003, that would end up in the first partition. Why is that? Because my partition function, the first year I put was 2004. So I put January 1st, 2004 as the first partition in my partition function. Anything before that will go in what's called the first partition. Okay? So that January 1st, 2004 defines the boundary between my first and second partition. Now I created a right partition, so that means that the value January 1st, 2004 would go in which partition? 2, not 1. If it was a left partition, the value January 1st, 2004 would go in partition 1, and a millisecond later would go in partition 2. That's why right here when you see 2004, that ends up in partition 2. 3, 4, 5, 6, and so on. So the last year that I put was apparently 2007. And then, of course, right now, any 2008 or 2009 data would also go into that sixth and final partition. Now I'm going to run a very similar query, only I'm going to basically get the count of records in my partition table that fall within each partition. Okay, so you can see I'm doing a group by that partition column. I'm ordering by date, and what I should see is that partitions 2, 3, 4, and 5 have data. Partition 1 has no data in it. So I didn't load any data that was earlier than January 1st, 2004. Okay, so I don't have any data for 2003, I don't have any data for 2002. Likewise, I also, the largest value that I have in there is December 28th, 2007. So I have new 2008 data, 2009 data. Okay, so what I'm going to do now is create basically a duplicate table that matches my partition table in structure by just doing a select into. And what I'm doing is going to fill it with 2008 data. So you can see what I'm doing here is saying, give me everything that's 2007 for my partition table and add a year to its date. What I should end up with is about 1.3 million records with dates of 2008. Okay, and we're going to use this for switching. I'll show you that here in a minute. Now what I'm going to do is actually modify, I'm going to create some indexes here so that my structure of my non-partition table matches my partition table. Now this is important because in order to do efficient switching, merging, and splitting, the physical structures have to match. That includes columns, data types, nullability, indexes, etc. Okay? So I can show you here. I'm going to do just a select top one from my newly created table and account. You can see I have about 1.376 million records, and they all are in the 2008 date range. So they're all from January 1st, 2008 and above. Okay, and I got about 1.3 million of them. The next thing I'm going to do is on that table that is not partitioned, I'm going to create a check constraint. And I'm going to create a check constraint that says that I know that the date time is greater than January 1st, 2008 and less than December 31st, 2008. Now, this is another important step because this allows the optimizer to know, without looking at that data, that it matches a partition of 2008. Okay, if I didn't put this, the switch or merge or whatever would still be efficient, but it wouldn't be as efficient. Why? Because SQL Server would have to scan all the date time values in that non-partition table to make sure it would actually fit into a partition that I'm going to push it into. Okay? I'm going to create that constraint. It takes no time. So now we're going to actually do our first switch. And what I'm going to do is, again, I'm going to query, just to give you a refresher, These are the partitions that the partitions in my partition table and the number of records in each one. Okay, so you'll notice that it's 2 to 5. I have no 6 partition. I have no 1 partition. Now what I'm going to do here is switch data from my unpartitioned table into my partition table, and I'm going to put it in partition 6. Now partition 6 is empty, I know that. Partition 6 also, the database engine knows, should only contain data for 2008. Okay? Now if I were going to do this without switching, I would have to do what? An insert statement. How long would an insert of 1.3 million records take on my little dinky laptop here? It would take at least 30 seconds, probably more like a minute and a half. So let's watch how quick this is. It's a simple metadata change. Boom, it's done. So we just took 1.3 million records and in a matter of milliseconds moved it from my unpartitioned table into my partition table, into an empty partition. To prove that, let's run the same query again. And you can see now that partition 6 will show up with 1.37 million records there at the bottom. Okay, and in our partition table right now, we have data for 2007, we have data for 2008, we know that. We have no 2009 partition right now. Our 2008 partition boundary is our last partition boundary. So right now, the last partition in our table has data in it. As a best practice, we always want to keep an empty partition on both ends of our partition table. So what am I going to do? I'm going to split that last partition into 2. And what I'm going to do is split it on the January 1st, 2009. What that will do is create a new empty partition at the end so that the next time I want to switch 2009's data in, it will be very fast and efficient. Now notice again, I just ran that under a millisecond. It split that data. Why does it take so little time? Because it knows, based on the partition boundaries, that 2008 data is all I have. Okay? Now let's run that same query again, and we should now see that our 2009 data flows into partition 7 as opposed to partition 6 like it would have before. And if we run our other query, it should be exactly the same. We still only have 6, partition number 6 going up to 2008 because that's the last partition that has any data in it. So now let's go in the opposite direction. Let's take data from our partition table and move it out. So if you take the rolling range scenario, what we just did is put in today's data, and now what we want to do is take out 90 days ago's worth of data. Okay? So basically, I want to take that partition 2 and get rid of it. Similar, if I were doing this without switching, what I would do is a delete statement. Delete from this table where the date time is between January 1st, 2004 and December 31st, 2004. And how long would that take? Again, it would take 30 seconds, maybe a minute and a half, maybe more. And people would be blocked, and you'd have all kinds of trouble. So what I just did is empty my unpartitioned table, the one that had the 2008 data in it. You can see it's empty now. Okay? And all I'm going to do is run this other switch statement, and it's going to go in the opposite direction. So I'm going to take data from my partition table in partition 2, and I'm going to switch it into my empty unpartitioned table. So again, I'm going to take 1.37 million records from 2004 and move it into my empty table. And again, if I run it, took a millisecond. And just to view the data, you can see that my unpartitioned table, here's the count at the top, now has 1.37 million records in it, and it definitely contains data. Okay? If I query my partition table, I should no longer see any data in partition 2. Partition 3 should be my first. Okay? So I've just now deleted 1.37 million records in a matter of milliseconds. So take your loading scenarios, and you just shaved off, the inserting of 1.3 million records and the deleting of 1.3 million records. That's going to be a significant, not only time savings, but also drive your concurrency up because other people won't be blocked from running simple queries or doing other things. Okay, so now what I'm going to do is add a constraint to my unpartitioned table saying that the data is only 2004 data because that's the data I just took out of my last partition into my empty table. And then just to show you, again, I'll run this query, and just to show you that inserts and your typical things still work, you can see here that partition 2 still has no data in my partition table. I'm just going to insert 50 records from my unpartitioned table, which is data from 2004. I run that insert. That worked fine. If I run a query against my partition table, you can now see that partition 2 has 50 records in it again. And I can do a delete also. So I'm going to delete for 2004. That deleted those 50 records. And of course, the partition 2 should be empty. All that was to show you that inserts, deletes work just like you normally do today. The storage engine takes care of worrying about where to put them and where they should go. Okay. So now let's, what we're going to do is now we've emptied our first partition. And now what we have is 2 empty partitions on the beginning of our partition structure instead of just 1. There's no need to have 2. So what we're going to do is merge those 2 into 1 so that we have only 1 empty partition on the front and 1 empty partition on the back. Okay? So if I show you right now, you can see that the last partition I have is 2004, and my 2002, 2003 data still goes in that first partition. What I'm going to do is run a alter partition merge statement. I'm going to merge that range on the January 1st, 2004, which was the same value that I used initially to specify my initial partition boundary. I'm going to run that. And now I should remember before when I ran this, partition 3 was the first partition that had data. Now, even though we haven't loaded any 2004 data, all that data has moved into the second partition. Why? Because we merged partition 1 and partition 2 into 1. So what was partition 3 becomes partition 2. What was partition 4 becomes partition 3, so on, so on, so on. So we don't have any 2004 data in here. It's still 2005. It's just that we merged those partitions together. Okay. Now I'll quickly walk you through using those same, just some quick indexing. I'm not going to run the first one because it takes about a minute. But what I'm going to show you here is the time savings that you can get by rebuilding or reorganizing a single partition as opposed to your table as a whole. This first statement rebuilds the clustered index on my partition table. And it takes just over a minute to run on my laptop. Okay, trust me, I ran it about 4 times before we started the demo. Here, what I'm going to do is rebuild the clustered index. Actually, this was an online cluster rebuild. An offline cluster rebuild takes about 13 seconds. Again, a non-clustered index online. Here we go. Okay. So now let's start working with partitions. One thing to note, I think this was in the slide deck, but you cannot rebuild a single partition online. So if I try to run that, I get an error. Online rebuilding is not supported for a single partition. Okay? You can rebuild a single partition offline. You can also reorganize a single partition, okay, which is an online operation always. You cannot rebuild any type of index online for a single partition. But I can do an offline rebuild for a single partition. And compared to my minute, just over a minute that it takes to rebuild my clustered index online for the entire thing, if you'll notice it took 4 seconds to rebuild just a single partition. Okay, so concurrency probably wouldn't be impacted much there anyhow. I can do the same thing. This is a reorganization of a single partition instead of a rebuild. That should take about 7 seconds. 9. And I can also do a rebuild of a non-clustered index. And again, that took less than a second compared to 13 seconds that it takes to rebuild my entire non-clustered index. So obviously, if you multiply this out from, what am I at, 5.5 million records to 5.5 billion records, or that type of scenario where you have lots of data, the savings that you can gain in terms of just sheer index maintenance time are quite substantial. How are we doing on time? 10 more minutes? Okay, good. Okay, now the next thing I'm going to run you through is some differences in query execution. So most of the time when I ask people, why do you want to partition your data? The first response I get is to make my queries run faster. Well, sorry, that's really not where you're going to see a large benefit when you partition your data. Partitioning data is all about managing and maintaining and bulk loading like you just saw. So you can take bulk load operations and shrink them from hours and hours to milliseconds. What you can't do, or what partitioning will not do for you, is take queries that run in 2 seconds and run them in 2 milliseconds. Many times people think, well, if I partition my data, all my queries will just start running faster because they'll magically run against a smaller data set. Well, though that might be true, in some cases, it's not true in other cases. So what I'm going to do is run you through some scenarios here. I've loaded a table with about 602,000 records, so not any substantial amount of data by any means, but it gets the job done here. And what I've done is partitioned it on what would mimic a state column in the United States. Okay, so you can see that I have some for California, some for Florida, some for Georgia, etc., etc. Okay, and to show you that I have, what I have is I have about 86,000 records for each state, and I have about 7 states with data in it. Okay. Now, just like I did before, I'm going to, I have that table I just showed you is partitioned on state. What I'm going to do here is build an exact replica of that table with the exact same data, the exact same schema, the exact same indexing. The only difference will be that it is not partitioned. Okay? So at this point, what we have are 2 identical tables. One is partitioned and one is not partitioned. They each have like an integer, a character column, and a state column. Okay? Exact same index structure and everything. Now, what the first scenario I'm going to run here is I'm going to run a query that does not filter on the partition column. Okay? So my partition column is actually called partition column, and you can see I'm not filtering on partition column anywhere here. All I'm doing is a filter on my ID between 10 and 100. And although that's going to be very efficient, against a partition table, we'll run this 2 or 3 times to get and take an average so that we get a cache. So that's just over 3 seconds consistently. Okay, and if we look at the I/O that it's performing, each operation is performing about 8 scans and 14 logical reads. Now those 8 scans are no coincidence because we have 8 partitions on this table. So what happens is those aren't scans of lots of data, it's just constant scans of metadata saying, how many partitions do I have? And then it has to seek into each of those 8 mini B trees to get all the data that matches. Why? Because you're not filtering on a partition, so the optimizer has no way to know to exclude particular partitions. Okay, so that took just over 3 seconds. I'm going to do the exact same thing on my non-partition table. And you can see that it consistently runs just under 2 seconds, as opposed to the just over 3 seconds on my partition table. So what this is this is a query that performs a seek into an index, a very efficient seek into an index. You can see that just by having a partition table versus a non-partition table and not filtering on the partition column actually introduced about 30% overhead. Okay? So that's interesting. So the non-partition table wins that scenario hands down. Let's do something else, and this time we're going to do the same exact query. You can see everything's the same. The only difference is we're actually going to filter on the partition column as well. So I'm going to say where the partition column equals California. So the optimizer in this case should be able to rule out 7 of the 8 partitions and just scan the 1. Okay? So let's see how it performs. I'm going to run it a couple times here. And what do you see? About the same execution time. Okay, it's still about 3 seconds. You can see it's doing only 1 scan now. So it ruled out the 7 other partitions. But it's still taking about 3 seconds, just over 3 seconds to run. If I run the same exact query against the non-partitioned table, you can see that it takes about the same time, 3 seconds. Now, a lot of people get surprised and say, well, we added an additional filter, why does it take longer? Well, the reason it takes longer is because the index on this fun detail ID doesn't include your partition column value. So for every record that matches, the database engine has to take additional CPU cycles to actually determine, well, does that actually match California? So in that scenario, at best, it was a tie. So your partitioning still didn't give you anything, even though you were filtering explicitly on a single partition. Okay? Now what we're going to do is, well, I'm going to skip this one because that's just saying if we added a covering index. And that's what I was just talking about. Okay, now in the same exact scenario, what if we did, instead of an equality, so last time what we did was equals California. This time we're going to do greater than or equals California. So instead of an equality operator, we're going to do a non-equality operator. Okay, so I'm saying the same exact thing, only instead of equals California, greater than or equals California. And we'll run it first against the partition table. I'll run it twice to verify the cache. What do you see? You're at about just over 4 seconds. We're doing 7 scans and 14 logical reads, so about the same plan and the same times as the initial one. Let's do the same exact query on the non-partition table. And what do we get? About the same time, just over 3 seconds. So again, tie. Okay, so your partitioning still hasn't given you any benefit. It's actually giving you a detriment for some queries. Okay? Now, what are we doing in this one? Okay. Here we're going to try in a scenario where we're doing a scan. So instead of a seek, all the other ones have been a seek into an index. This time we're going to scan the table in its entirety. So what we're doing is filtering here on this filler column. There's no index on that column or anything. So the database engine is going to have to scan the entire table to try and figure out, what records match that. So we're first going to go against the partition table. And then what happens? About 2 seconds. Again, we scanned all 8 partitions, and we did about 14,000 logical reads. Okay, let's do the same thing on the non-partition table. What do we get? Again, the same exact time as the as the partition table. So again, no benefit from partitioning. So a lot of people at this point are asking me, well, where does partitioning help you with query execution? Okay, so we all know that partitioning can help you a lot with loading data, maintaining data, managing data, etc. So far, all we've seen is it hurts you at best with query execution. Well, here's where it can help you with query execution. And what we're going to do is, again, we're going to do a scan of the data, only this time we're also going to include the partitioning column. So we're going to do a scan, not a seek, but we are including a partitioning column. So on our partition table, the database engine is going to be able to exclude 7 of the 8 partitions, or 7/8 of your data, and scan only 1/8 of your data. Whereas the non-partition table is going to have to scan all of your data. Okay? So if we run this on the partition table, you can see that it finishes in about 700 milliseconds. If we run the same exact thing against the non-partition table, you can see this is much longer. That was almost 5 seconds. And this one should be about the same, almost 5 seconds. So where does partitioning help you with queries? Large scans of large tables where you can filter out some of the partitions explicitly. Where is that common? Data warehouses. Okay, so data warehousing is where partitioning can help you with your data warehouse type queries where you're scanning large amounts of data. Your OLTP systems where you're seeking, writing small amounts of data, reading small amounts of data, partitioning isn't going to help you for query execution. Okay? So we're under a minute. Any questions before I let you go? Go ahead. So the question is, if you were to partition an existing table, is it transparent to all applications? That answer is yes. Nothing has to be changed in terms of your database code, your .NET code, or anything. Is it possible to roll back? So basically, is it, if you partition a table, can you unpartition a table? Absolutely. Basically, what you do is you end up having to recreate the clustered index on the table. So to partition a table, an existing table, what you would have to do is build your partition function in your partition scheme, and then recreate the clustered and non-clustered indexes on that table in the partition scheme. Okay? And then if you want to unpartition your table, you basically do the same exact thing, only instead of rebuilding your clustered indexes on a partition scheme, on a file group, or whatever you would normally do today. Yep. So that's your rollback. Obviously, you could also do a backup restore. You could do a backup before you take, but of course then you're going to lose data if people are probably using it. So, yes. So is the question, if you have a clustered index, the data, and it's partitioned, the data is stored in separate file? So a clustered index, if you have a partition table and a clustered index that's built on a partition scheme, the data is stored however your partition scheme defines. So for example, if in my scenario here where I had a table with a clustered index, and I built that clustered index on a partition scheme that mapped a single year's worth of data to a file group. In my case, I did it to all one file group. But if I had done that to file group 1, the data for year 2004, for example, or the clustered index portion that was 2004 would have resided on file group 1. The clustered index portion for 2005 would have resided on file group 2, and so on and so on. I guess I'm not understanding the question. Can you have a clustered index that is made up of multiple columns? Yeah, oh, okay. So can your clustered index be on something other than your partitioning column? Absolutely. But with a clustered index, your partitioning column has to be included in the clustered index. So for example, in my case, I could have had a clustered index on the ID and then the partition column, or the ID and name and then the partition column. Has to include the partition column, but it doesn't have to be the primary or secondary value in your index key. Now, non-clustered indexes, it doesn't have to be part of the key, it just has to be included. Can you update the value of the partition column? Absolutely. Yep. All it will do is transparently move from partition 1 to partition 2. That's correct. Yep. One other quick thing I wanted to mention in terms of what I answered here, which was to partition an existing table, you basically recreate your clustered indexes on a partition scheme. With 2005, you can obviously do that online as well. So you can rebuild indexes online in SQL 2005. So end users of your OLTP system, for example, wouldn't be blocked for however long it takes you to build your cluster index or unbuild it. Okay, so that's if you're running Enterprise Edition. So one catch. Yeah. So how can you improve the response time? For seeks. So it depends on what you're asking. If you have an OLTP system and you want to improve the response time to queries that your OLTP system runs, I'm going to assume that you're already tuned, you have the appropriate indexes and whatnot. Because in an OLTP system, the way you tune is basically indexes for your reads and associated indexes for your writes. In an OLAP system, a data warehouse, partitioning will improve 99% of the queries. Because in a data warehouse, you're usually performing large scans, not seeks.
Yeah, that's fine. That is fine. But slice and dice, we can definitely improve.
Yep.
Online application.
Yep. How can you improve the indexing? That's really your golden bullet, so to speak. There's obviously other things you can do as well. It might be changing the design of your infrastructure. It might be changing the code, rewriting your whatever. But indexing, in terms of partitioning, will not help in terms of response time to your LTP system. But there's at least 50 other things that you could do. So the better The better question would be, given information that you'd have to gather through capturing, monitoring information and whatnot, what should we do? And that answer might be add some indexes, it might be change this T-SQL statement, it might be change your table design, it could be 100 different things, I guess. Partitioning is an enterprise-only feature. Yes. Yep. And developer. But, okay. Thank you very much.